In this lecture we introduce absolute values. So an absolute value on a field K, this is a map going from the field K to positive real numbers, and it satisfies the following three properties. So here x is in the field K. So absolute value of x is greater or equal to 0, and this absolute value becomes 0 if and only if this x to start with was 0. Then you have the multiplicative property. Absolute value of xy is absolute value of x times absolute value of y for all of xy in the field, and absolute value of x plus y is less than equal to absolute value of x plus absolute value of y. So this is called the triangle inequality. So if these three conditions are satisfied, then our absolute value is called Archimedean. So sometimes instead of 3 we will mention another condition, 3 prime. So an absolute value on K is called non-archimedean if it satisfies this 3 prime instead of 3. So this condition 3 prime, the following condition, this is called the ultrametric inequality. So this is x plus y is less than equal to, so you have to choose either max, either x or y. So you have to choose maximum of these two. So whatever is maximum, you choose that. So notice that this is actually a much stronger statement than this, and this 3 prime implies 3. So this 3 prime actually implies 3, and this you can see immediately. So some remarks here now. So first remark is that absolute value of plus or minus 1 is just 1. So therefore absolute value of plus or minus a would just be a. Another thing is sometimes this triangle inequality is written like this. There is a constant c put here. You put a constant c here, constant c here, and constant c here instead of 1. So for our purposes we will just take this c as 1, but sometimes this constant is also put up there. So now let us come to some examples. So first example is our field K is just rationals, and the absolute value is just our usual absolute value, and our usual absolute value we write it by writing infinity here. So our standard absolute value which we use in real numbers. So second is the absolute value of a complex number, and this is absolute value of a complex number is different from the usual value because this is the distance formula for our complex number, which would be a plus ib. So square root of a square plus b square. So example number 3 is that we can also define absolute value via embeddings of a number field K. So say sigma is the embedding of our number field into complex numbers. Then we have a valuation like this. So you have a valuation sigma here, then this is sigma x. You're taking the this complex value here. So sometimes this is also square because it could be written as sigma times sigma conjugate. In fact, all the valuations which live on these number fields, so you could ask how many different valuations can I put on a number field, and the answer is precisely as many embeddings as you have. So number 4 is our famous p-adic. So K is again rationals, P is a prime number. So you take an x which is non-zero in rationals. So the p-adic valuation is like this. You first write x as p to the power of some alpha m by n, and this p prime does not divide m or n. Then the valuation at this prime p is p to the minus alpha. So this alpha is coming right here, and p does not divide m times n. That means p does not divide m or n. Now this same thing we can do for elements in Dedekind domain. So this above example is generalized to Dedekind domain, say D, and this Dedekind domain has a field of fractions K. So you can now consider an element x which lies in the units of K, and set order of p as the power of p appearing in the factorization of x in D. Just like here alpha was appearing, here order of p is appearing. So in fact this alpha can also be called order of p. So now our valuation is again xp is just like we had p to the minus alpha, here you have minus order, and this n of p is nothing but norm of an ideal p. So this is norm of an ideal. So norm of an ideal is actually easier to define than a normal norm, because this is just the cardinality of the set D modulo P. So if from your Dedekind domain D you modulo out our ideal P, whatever you have left you take its cardinality. So this is a number, so this thing would be a some constant, say C. So this will become some constant because it's a cardinality some number, and then you raise this number to the power of minus order P of X, which is nothing but the power of P appearing in the factorization of X. And finally we can talk about trivial absolute value. So you just take absolute value of X as 1 for X not equal to 0, and for X equals to 0 you always have this statement here. So we want to distinguish Archimedean from non-Archimedean values. So for that we have this lemma. So this absolute value is non-Archimedean if and only if you take absolute value of n, which is an integer. This is bounded. Now first in this direction we start with norm being non-Archimedean. So first this is true for all norms whether they are Archimedean or not, and follows from right here. So we may assume n is greater or equal to 1, and you can write this n integer as 1 plus 1 plus 1 so on. So now we use this condition because we know it is non-Archimedean. So all of these are 1 here, so maximum is 1, so this norm n is bounded by 1. So you start with non-Archimedean absolute value, you came up with the bound. Now we go in this direction, this is bounded, so bounded means that this absolute value is bounded by b for some n as an integer. So now see that absolute value of xi times y to the m minus I, this is obviously less than equal to max of absolute value of x, and whatever the maximum is you raised it to the power of m. So you multiply this I with m minus I will cancel out, m will remain. So this holds. So now you use the binomial theorem. So this thing is bounded by this portion which I have copied from right here. This we are saying is bounded above by b. Right here all these integers, because all integers are bounded, and we are summing this up m plus 1 times, so 0 to m. So this sum becomes m plus 1. So now you take mth roots, so this becomes 1 by m, so m by m, this becomes 1. So you have this, and now as m goes to infinity you take higher and higher powers, this will go to 1. So you get x plus y is less than equal to max of this, which is what we wanted to show. So this leads us to a new definition. So an absolute value on a field K is Archimedean if K has character 0 and if there exists m an integer such that this absolute value of m is greater than 1. So there has to be some integer for which our absolute value has to be greater than 1. So if it is not greater than 1, it will be non-Archimedean. So notice this character 0 here is important for absolute value, because otherwise we will just get a trivial field. So say if xn is 1, and this can happen when you do not have a field of character 0, then absolute value of xn would be 1, and which would imply that x is 1. So you just get a trivial field here. So that's why we are putting in character 0. So now we have an absolute value on a field K, or we have a non-Archimedean absolute value. In any case, once you have an absolute value, this absolute value gives you a distance function. So absolute value gives you a distance function. So this distance function, you can say distance of between 2 points x and y is given as this absolute value, which may or may not be Archimedean. So once you have a distance function, you can talk about open balls around points. So once you can talk about open balls around points, you can talk about their topology, just like we did this in topology or analysis. So now we will discuss some properties of non-Archimedean absolute values. So let this be a non-Archimedean absolute value, And if a is not equal to b, then a plus b is equal to maximum of either a or b. So geometrically this means that every triangle is isosceles, and this we can show easily. So you just suppose that b is strictly less than a. So then the ultrametric inequality, this right here, instead of xy we are writing ab. So a plus b is less than or equal to max of a and b. So then absolute value of a, you can rewrite it as a plus b minus b, which is less than or equal to, again, ultrametric inequality right here, max of a plus b, b. But max of a plus b here is less than or equal to max of a or b. But a is bigger than b, so here it is just a. So that's what you get, a. So this is now surrounded from two sides. It is less than or equal to a right here, and this shows that it is greater or equal to a. So you have that a plus b is equal to a, which is actually max of a and b because we have set b less than a. And as I said before, geometrically this just means that every triangle is isosceles if you have a non-archimedean absolute value. So an important corollary of this is that every point of an open ball, if you use this non-archimedean distance function now, will be a center. So say BAR is an open ball centered at A. So say you have some ball here and the center point is A, and B lies in this ball. So B lies within this ball right here. So then for any x again in this ball, so you have another x in this ball, we have distance between x and b, so distance between this. So now we are using ultrametric distance. So this is ultrametric absolute value, but you can rewrite it as x minus a plus a minus b. Now both these two would be less than r because r is greater than the maximum values. All these three lie in a ball of radius r. So x minus a is less than r, a minus b is also less than r, and therefore r is greater than the maximum of these two. So that is it. So you get r here, or you can say that this is equal to maximum. Here is maximum, there is an equality here, this is equal to maximum of either this or this, but both of them are less than r. So therefore now x would lie in a ball B with center B and radius r. So x lies within the ball because distance between x and B is less than r. So just this thing being less than r means that x lies in this. So this is true for all point x which lie in the ball here. So therefore ball centered around A lies within the ball centered around B, because all points x which lie in this ball, because of this statement right here, they also lie in the ball here. You can reverse A and B, giving you the reverse inclusion, which is you will get equality. So if you have a ball like this BAR which is centered at A, and there is some point B in this ball, that can also be considered as the center of the ball because we have a ultrametric inequality which shows up right here. So if it was an Archimedean value, then this would not be less than r, because this could be something close to 0.9r, 0.9r, it could become 1.8, but this is less than r precisely because we have non-Archimedean or ultrametric inequality. So now important remark is that ultrametric inequality makes the space completely disconnected. So the only points of the space which are connected are singletons. Singletons are the only connected subsets. So you can always form disjoint balls around 2 points A and B by choosing the radius which is half of the distance between them. So ultrametric inequality ends up giving you a completely disconnected space.